Hey, what's up, guys? Today we're going to take a look at proportions. And before, in a past video, we talked about ratios. And proportions we use it's a statement that two ratios are equivalent. So before we used a example, and I'll just use it again, of if you're in a class, and I'm just going to jump right into ratios, so if this doesn't make sense, you're going to need to watch the rates and ratios video. But if I have a ratio in a classroom of 1 teacher to 27 students, so that's my ratio. When we do proportions, we use the fraction form of it. So 1 over 27 is my fraction for that. Now, let's say that that is the teacher to student ratio for the whole building. And then let's say that the building has, let's say so this is for the whole building, the ratio for the whole building. But the building has 576 students. And you want to know how many teachers it has. So we can use proportions to solve that. So if the whole building ratio is 1 teacher to 27 students, that ratio is going to hold true no matter how much you scale it up. So here we have teachers on top and students on bottom. And we have to keep that proportion the same when we go over here. So the building has 576 students, so students go on bottom. And we don't know how many teachers there are, so it's X on top. Now we solve these by cross products. So how we do it is this, we'll cross it. So 1 crosses down to 576, and we multiply that. So we write 576. The equal sign stays in the middle, and then we cross product this one. 27 times x, which is 27x. So now to solve it, it's just a regular algebra problem, and we divide both sides by 27. And you're going to get 21.33 repeating equals x. So that's our answer. But think about it. We're trying to find what? Teachers. Is there ever going to be 0.33 of a teacher? No. So that means that there are 21 teachers at this building. So, again, cross products is how we solve these. It doesn't matter which one you do first. It doesn't matter if you go bottom left to top right. As long as you cross product one, stick the equal sign in the middle, and then cross product the other, and then solve it like an algebra problem. So our final answer was 21 teachers, and that's just a quick example on how to do that. Let's look at other applications of proportions. So proportions are also great in geometry, and then in turn we can apply the geometry part of it to a lot of real world examples. So let's just look at the base geometry point of it. So let's say that you know that two triangles are similar. And similar figures have exactly the same shape, but not the same size. So they may have been scaled up or scaled down. But let's say that and this is how you'll see it, triangle, and we'll just call it RST, and then this means similar, the symbol in the middle, squiggly line, is similar to triangle BCD. And then you'll have your two triangles, and then one will just be bigger or smaller than the other. Pardon me for my bad triangles there. So RST and then CBD. So we know those two triangles are similar. And then they'll give you the labels for them. So 5 feet and then 8 feet. Let's just do X feet and 12 feet. And they want to know how long the segment of X is. Well, as you can look, just looking at the figure, you can see that this is lined up fairly well. You can see which line segments correspond to which. But there's going to be times where they try to trick you, and it's not that simple to see. So what you do is, let's look at X. X is on the line segment BC. Up here in this triangle, BC came first. So it has to be similar to the other triangle, and here in this triangle, RS came first. So the line segment RS is the one that corresponds to X. It's pretty easy to see that visually now, but other triangles, rectangles, they really can mess you up if you correspond it to the wrong side of the triangle, because they'll flip and turn the triangles and confuse you. So again, BC corresponds to RS. So the length of BC is X. And then on that same triangle, X to 12. And then as long as you put the same corresponding sides on top to bottom, it should work. So 8 feet corresponds with X. So it'll go on top over 5, because that was the other line segment there. So we cross multiply. So X to 5, we have 5X. We stick that equal sign in the middle, and then 12 to 8, which is 96. And then we divide both sides by 5. And we're going to get X equals 19.2. So this line segment here is 19.2 feet. Now there's one way to do it, where you put each proportion deals with one triangle. So this was one triangle, this was triangle BCD, and this one was the sides of triangle RST. Now you could do it another way. You could use it in terms of comparing sides. So I'm going to see if I can fit it down here. So let's say we're going to start with X first. And this is where you kind of deal, it's which makes more sense to you. So X corresponds to what? 8. So you can put X is to 8, or X to 8 equals, and then 12 corresponds to 5. And since X, you have to put X and 12 on the same top part because they're on the same triangle. So as 12 is to 5. So I did X is to 8 as 12 is to 5. And I put an equal sign in. That's how I speak that math. So we cross multiply, we'd get 5x is equal to 96. And as you can already tell, we're going to get the same exact answer. X equals 19.2. So really just choose the way that seems best to you, where here the top parts matched up to the triangle BCD, and the bottom parts matched up to triangle RST. So that's two ways to do those. Let's see if we can look at another example. Yeah, I can probably fit another example in before I run out of time on my recording. So, real world. Let's say you walk up and you see a giant tree. Not really, just a large tree, and you don't really know how tall it is, and you don't feel like climbing up with a tape measure, or multiple tape measures, measuring it. But what you can do is you can measure its shadow, which is much easier than measuring the height of the tree. So let's say you have your tree. I'm an artist in my off time. Okay, there's your tree. Again, I recommend always drawing. When you read a word problem, draw as you go. First off, it's fun to mess around and show off your drawing skills or lack of drawing skills. And two, it helps you see the problem. So you have a tree. You don't know how high it is. That's what you're trying to figure out. So that is X. But it does cast a shadow. And here's my version of a shadow. That is 45 feet long. You look at yourself, and you know that let's just use 6 feet because that's an easy one. You know that you are 6 feet tall. This is definitely not to scale. And your shadow that you cast is 3 feet long. And those would be two really easy things to measure because you know your height and you can quickly measure your shadow. So we have a tree, don't know how high it is. Its shadow is 45 feet long. And then you are 6 feet tall and you cast a shadow of 3. So those would be proportional because no matter where you are, each person's shadow would be proportional to its height. So let's look here. I'm going to do the way where we correspond each fraction to its own shadow. So we got X here, and that's the height of the tree that we don't know. And the tree casts a shadow of 45 feet, so X to 45. And that's going to be proportional or equal to the height of the person, which is 6. I put both heights on top. And then the shadows both go on bottom, so 3 feet here. So we cross multiply. 3 to X is 3X. The equal sign gets stuck in the middle, and then 6 times 45 equals 270. And then we divide both sides by 3. And X equals 90. What was our units? Always remember that. Feet. So that tree is 90 feet. You can do that with buildings, trees, anything that casts a shadow. As long as you know your height and can measure your shadow, you can find the height of very tall buildings if you feel like measuring how long the shadow is. Or just anything. Because shadow is going to be proportional to its height. So, thanks for watching. This was a longer video. If you have any questions, want any more videos that I haven't done, put some in the comments. And thanks for watching.